So the complication introduced by these serially correlated shocks is just that they introduce continuous elements in the state space that we need to take into account. All right. So as we saw earlier, the Emacs functions have to be calculated for each point in the state space. And when the variables take on only a finite number of discrete values, so for example, years of schooling, number of children, then the solution is just going to be to solve for the Emacs at each of those possible combinations. But if it's a continuous variable, then obviously you can't do that. You could also have more complex models where even if you have all discrete variables, just the state space is expanding so much that it becomes computationally hard, even when everything's discrete. And this was called the curse of dimensionality, and this was something that even Bellman talked about. I mean, of course, I don't know how they solved these models at all. In the 50s, just more computers. So, but I mean, now as computers get better, of course, you can deal with more choices and larger state space. But still, the state space can get really very large. So we need to have some methods of dealing with these large state spaces. Okay, so there are two ways that people try to accommodate this. And one is you can just keep the model simple. So just impose a lot of discipline on yourself when you're writing down the model, to make sure that when you take it to the computer, you can actually solve it within reasonable time. And people have different ideas of what reasonable time is, because I know like Ken Wolfen has had models that I think took him 5 years to solve. And that's not my time frame. So 5 years is too long. But you have to...
That's last thing, 7.
But you have to decide what's reasonable for you. I mean, normally it won't be solved in 1 day, no matter what, but so for me, 1 year is maybe reasonable, but even that's a long time. So if you want to have a model that's solved within a few weeks or a few months, of iterating on the likelihood, you have to keep it kind of small. Or you can use some approximation solutions to getting these Emacs. Okay, and in terms of approximation solutions, there's a whole sub-literature on different types of approximation methods. So one is you can discretize the continuous variables and just solve the Emacs functions on the grid of discrete values. So you could modify the law of motion so they stay on the discrete grid. So assume that something's Markov, say, with just a discrete number of values it could take on. Or you could just evaluate the functions on the grid points, but then interpolate between the grid points. Like not assume that they actually take those values. So for example, if I estimate a model of savings decisions, like you could have continuous savings decisions, but I might assume that you can save 0%, 5%, 10%, so that you have a finite number of savings values. Okay. So there's an older paper that originally proposed approximating these Emacs functions. Keene and Wolfen applied the approximation methods to the types of models that I'm describing here. So this is another alternative. So here you can actually draw randomly some subset of the state points. So instead of just putting it on a discrete grid, you could randomly draw. So for example, if you had like 1 million state points, you randomly draw 100,000 or 500,000, or something that would reduce the number of state points. And you don't just want to draw state points that are in your data, you want to draw also state points that are not in your data, because your model, you're evaluating choices, the utility of choices that were not made. Right? So I think I'm going to turn this off. So that's not good.
I got it done. So shout.
Yeah. Okay. So you want it to cover the whole state space when you draw the state points. Okay, so, and then you can interpolate. So one option is to just do regression interpolation. So you draw some subset of the state points, you evaluate the Emaxes at that subset, and then you just regress the Emax values on the omega, or the omega minus, and there you have to make another functional form assumption, like linear regression. Do you introduce the state points linearly or maybe squares or whatever? So that's like a little regression that goes along with your estimation. But that would allow you then to interpolate at other values of the state points. So if you need it at different values, you can just use the regression interpolation.
Is there kind of a way of choosing these discrete points that you're interpolating through, like in a more kind of intelligent way than just like kind of randomly picking them, or?
Yeah, so well, what I do sometimes is there isn't a good guide for exactly how to do this. Like you want to cover your state space, and then in some of these models, the state points are changing with time. So if you had a model of savings behavior, obviously very young people don't have very high savings usually, and then older people have higher savings, and the variance in savings is probably expanding. So a lot of times when I do it, I kind of simulate a state space over the life cycle. Like you can have simulated people where you kind of simulate different things that might happen to them in terms of fertility, savings, whatever you're modeling. And savings models are kind of tricky. Like I found that the Emax approximation functions do much better if the way you enter, say, wealth, because the major state space element is wealth, like in a savings model. And if you enter wealth in the same functional form as the utility function, that seems to do a lot better in terms of capturing the approximations. One thing you can check, and you do a regression interpolation, you want your R-squares to be like 0.999. You want super high R-squares to be sure that your approximation is good, because as you're solving backwards, if you have a crummy approximation at some time, that'll really affect all the previous times, So normally people would print out the R-squares, make sure they're very high, and not only do within sample R-squares, like you can also check, like use half the data for approximation and then compute an out-of-sample R-square for the data that wasn't used in estimation to make sure that it's also getting a good fit. And this part, I would say the part I don't like about this approximation is you're doing estimation here, obviously, right? And your results are going to depend on the quality of what you're doing here. But then at the end, when you do the standard errors for the maximum likelihood, and every time people ignore this stage, this is kind of this approximation, which is really an estimation, but it's just too hard to take it into account analytically in doing the standard errors. So normally it's completely ignored that you were doing this. Or at least under current methods. We don't have, like, in principle you could do bootstrapping or something, but that would be impossible computationally because you couldn't resolve the model for 100 bootstrap samples because it's hard enough to solve for the original samples. So, but normally people just check the R-squares, make sure they're super high as a check that the interpolation is decent. And there's another method proposed by John Russ. And this method I haven't actually tried yet, but this is something, his method requires continuous choice variables, let's see, as well as the state variables. So here's an example. So it doesn't fit exactly the model that we have, but you could think about making it continuous if, say, the probability that your experience, because labor market experience would be one of the state variables. So you could have a thing that if you work, this would be the probability of changing your experience. So it could be random, the extent to which working or not working augments your work experience. Right? So you could kind of convert it to a framework where everything's continuous. That if you work or don't work, that that this is random. But he shows then that if you evaluate on a grid, I mean, I don't know that much about this method just because I haven't used it, but it is one of the available methods. I haven't seen it used that much. But he comes up with this approximation method for the value function, and this is a grid of these randomly drawn state space elements, the different values of H, that are continuous, because the experience is continuous. And then, let's see, he proves that it converges, that the approximate value function converges to the true value function. And there's let's see, he has this notion that this is self-approximating. So if you want to construct a value function at a point that's not part of the grid, then you can form it this way. Like you evaluate it first at these grid points, and then these probabilities are coming from the H is continuous, and then you can approximate at other values outside the grid points in this way. And he calls it a self-approximating. And because any state space element can be reached from any other element with this probability P, the value function here you can calculate in this way at any element of the state space. So there are these different methods. The one I normally use is just the simple regression interpolation, and there is like kind of an open question about how you specify your regression, what's a good way of doing that. And I always check the R-squares, and then how you actually randomly draw the state space elements, given that your state space elements are changing with age.
So if you're doing a continuous approximation method, so one thing that I've heard of is Chebyshev approximations. Why would you? And it sounds as if that would be what you would want to do, as opposed to just this linear regression interpolation. Are you just not doing that because it's like complicated or?
Well, normally when I do it, it's not continuous state space areas. Usually I just have very large discrete state spaces. Yeah. But it's pretty much like problem dependent, like what's the best way to do it. Yeah. But you could enter any sort of approximation that you think is reliable and then check the reliability, at least with the R-squares. I would check within the sample and out of sample, like R-squared check. And you have to check that, because you're iterating. So it may be a good approximation initially, and then as you iterate on the parameters, the approximation could get worse. So you kind of have to check during the process of the iteration to make sure it's not becoming a crummy approximation over time or something. Okay, and there really aren't that many papers that compare, like we don't really know what are the best methods yet. Steinbrückner has a paper that compares several approximation methods. Keenan-Wolfman have a paper that does this interpolation, the regression interpolation method, with Monte Carlo data, where you know the truth, and then they estimate the model without interpolation, and then try it with different types of interpolation. And they find that the regression interpolation does pretty well in the model they studied. But of course, that doesn't guarantee that it's going to be great for other models. So we need more evidence, really, on what the best methods are. And there's also the question of, even when you're interpolating, how big a randomly drawn subset should be. Like if you have 1,000 state points, is it okay to have 1/10 of the total number? So that's another decision that you don't really fully know. So normally, I would check sensitivity to drawing robustness to different size subsets. Okay, so everything we talked about earlier was binary, but in reality, we'd like to be able to accommodate more than just two choices. Because I remember I told you that the papers in the 80s did two choices. So if you come with a model with two choices, you're going to have trouble getting it published, probably, because they're going to say, this doesn't really capture reality that well. because that was done in the 80s. So you want to do something that's a little richer. So we'd like to have additional choices, errors that possibly don't enter additively, you know, and then maybe relax, if we can, some functional form and distributional assumptions. So it's not hard to allow for more than 2 choices. So now, you know, as with like a multinomial logit model or something, now you have multiple latent variable functions. So that's instead of just having one, because now you have the utility. The probability that you choose choice 1 out of 3 choices, you have to have the utility of 1 exceeded the utility from 2, and the utility of 1 exceeded the utility from 3, right? So to do 3 choices, you need 2 latent variables, right? So I'll go through a more general model where we have a lot more choices and also have a fertility decision. I think these models are really nice for modeling like fertility because you not only model the number of kids people have, but also the timing of when they have kids. You know? So I've used these types of models for fertility decisions. Okay, so here's some data that we might use for this hypothetical model. So married women, so the only reason, I don't know why it's white. I think this is maybe data I can use in a paper, but it's probably just because we have intact households like husbands and wives, and you don't really want to have people on welfare since the model is not incorporating welfare as it is right now. But you could incorporate welfare. So the endless Y is a data set that's used for a lot of these models just because it's longitudinal. So it's a pretty long panel and it doesn't have a lot of missing data. So the model starts at the age of marriage. That we can assume the modeling period is 1 year because that's the period of the data. And so we're going to not only model whether she works or not, but also how intensively she works. So work less than 500 hours, work 500 to 1499 hours. So these are different working, kind of capturing full-time work, part-time work, or no work, right, to make it more realistic. And then fertility is going to be whether she had a birth during the calendar year, which means she got pregnant the year before. So usually you have to kind of, and in these models, you could assume fertility is a choice, or you could try to model that probabilistically, you know, that even if she wanted to get pregnant, maybe it doesn't happen exactly, or maybe there are accidents or something. So there are even models where people are choosing contraception, and then fertility is a function of contraception or whatever. But this one is just going to be a simple one where fertility is a choice. And usually before you start programming up this like complicated dynamic model, I just want to say that it's usually useful to estimate just some simple relationships between the choice variables and the state variables, just to make sure they're actually related. You know, because you don't want to spend a year of your life, you know, programming a 10,000 line Fortran program, and then in the end, you know, you don't even know if any of the things are related, or so you want to do a little exploratory analysis ahead of time to make sure that some of the relationships that you might expect to see are actually there. You know, so normally, even though I'm describing like how you estimate these structural models, there's a lot of work that's non-structural that people do, and even that they present in the paper. Like usually before just doing the policy results, you would also present just relationships between choice variables and state variables. You know, and those are non-structural relationships. But almost any non-structural estimation, you can also think of it as being a choice variable, a regression of choice variables on state variables. I think it's kind of a good way to think of it, even if you're doing non-structural work, because it gives you more way of justifying what are the variables you put in your regression. Like they should be the state variables that people are using to make decisions. Okay, so it's going to be similar to the other model, but now we just have the stock of children, and now there's an additional shock, which is a fertility preference shock. And we need more shocks because now we have more choices, right? So now we have these different shocks. So like the preference for working part-time, that would be a different shock here. Okay. And they're going to be serially uncorrelated, but we could incorporate these permanent types. Okay, and so this is incorporating the types. This is like the preference. These different preference shocks are all going to have this permanent unobserved heterogeneity plus the IID component. Okay, in the budget constraint, we might incorporate a cost of avoiding a birth. So this is mainly because the model is not capturing biology. You know, that women are more fertile at certain ages, and that's not in the model. And so if you want your model to fit the data, it's kind of hard if you're not incorporating some of these biological aspects. So this is kind of an artificial way of bringing it in, because you could have contraceptive costs that vary with the biological age of the mother. You know, that maybe like, you'll get a higher cost. This is the cost of avoiding a birth. So you'll maybe get a higher cost at younger ages, you know, when people are more fertile. So sometimes in these models you have to acknowledge that there's some aspects that are just not modeled. Or like if you're doing an education model, you know, where you're modeling decisions to go to school, lots of people end at 12. I mean, why is that? It's because high school ends at 12, right? Like, and then you have to go. So normally we put in a cost or maybe a utility of finishing 12 years, like a graduation effect. You know, and that's because the model doesn't capture the fact that, you know, institutional things, like the high school ends at 12, and that's why everybody's finishing at 12. So you have to sometimes put some things in the model to capture these things that are not already there. So it's a little artificial to say just contraceptive costs, but it's capturing fertility. Okay, and then just to make it richer than the earlier model, you know, there can be age-specific costs of raising kids that you might want to incorporate, and childcare costs. And the childcare costs may differ depending on how much the woman works, like if she works full-time or part-time. Okay, so it's just trying to be more realistic. It's not really harder than in the other model, but it's just there's some more parameters and we're trying to capture more realistically. So this is the, let's see, these are the different part-time work decisions multiplied by the wage. So this is now an hourly wage. This would be a childcare cost depending on, well, you could have different age classes of the kids. You know, so when kids go to school, then you don't have to have as much childcare because the school is taking care of them for most of the day. So you can capture all those things in the model. You know, but of course that introduces some extra parameters. So that's why sometimes people estimate models that have like 100 parameters. You know, a lot of it is just these sorts of things, trying to be more realistic. Okay, and the wage offer function now depends on how much she works. And we can log wages so that the error term doesn't have to be additive. Okay, this is just to be compact on notation, but this is the error, and the error can be non-additive in the utility function. Right? It doesn't have to have that structure we had before. Okay. And then husband's earnings, you could specify an equation for that as well. So it could be husband's age, husband's schooling. So you can see how the state space expands, right? Because now we have husband's schooling in the state space. Number of kids of different ages, like you have to keep track of that now. So that's all in the state space. So that's how even with discrete variables, you can get a large state space. Okay. So this is like number of kids of different ages. Right? And this is now experience. So she gets experience depending on how much she works. Okay, so now there are 8 choices for the woman because she can work different amounts and she chooses whether or not to have a child. So there are 8 total choices. So this is actually still a simple model compared to the types of models people estimate. And then after she can no longer have kids, then she only has 4 choices. So you have to pick, you know, whatever age, 45 or something, you want to pick an age for when she doesn't have kids anymore. Okay, so these are the value function. It's the same as we had before, and the only thing is that the number choice is different depending on her age. Okay. And then these are all the shocks. So she's got the wage shocks, the preference, wage shock, leisure shocks, preference shock for fertility, and husband's earning shocks. So 6 shocks here. Okay, now, you solve it backwards just as we had before. You have to calculate the Emax functions. But now the Emax is a 6-variant integral because we had 6 shocks in this model, right? So we're not going to get those unfriendly expressions, or friendly, but there's no easy closed form expression like we had before. What's your question? Okay, and then state space is all feasible values of all these things. So it's a pretty big state space. Okay, so dimension is finite but large. And this gives you an example. If a woman could get pregnant in 30 period, number of possible birth sequences, because we're keeping track of the age of the kids, you can see it's huge, right?
So I have a question about state space. So do we need to keep track of the specific age of the children for each children which was born to the...
Yeah, because you want to keep track.
Yes.
If you want the costs and everything to depend on the age of the child, then you do have to keep track of the age of the kids. I mean, you could, yeah, because even if you want to make categories, like you have to know when they age out of one category into the next category, and so it's not easy to make it simpler.
Yeah, that means the state space actually is even larger than the previous slides that we...
Yes, the age of the kids creates complications. Yeah.
Another question is that in this model, how do we deal with divorce? Like, if the wife changed husband,
Mm-hmm.
so
Yeah,
do we
you
need
can-
an explantation about the husband, like the evolution of the characteristics of the husband?
Yeah, some of these models incorporate like marriage and divorce. So you could have a model where a woman starts off single and then she gets marriage offers that arrive randomly, and she decides whether to marry the guy, and then divorce could be a choice in the model where you're deciding based on the value functions, you know. So you can incorporate all these things. Like you could have a model where she gets a marriage offer, she gets married, then she gets some other offer. You decide whether she's allowed to get offers while she's married. She can exogenously have divorce, or she could decide to leave her husband. That could be part of your model. You know, so you can incorporate all those things. But it's, you know, computationally gets hard.
Yeah, but just for this one, do we drop the women who change their marriage status? How do we deal with
You don't
that?
necessarily have to drop them. Like what people probably would do in this type of model would be to have a terminal value function. Like if people do things that are not captured, you could just say divorce is exogenous, there's some exogenous probability of being divorced, and when you see them, their future utility, like their value function, is going to be a function of their state variables. And so people would just estimate that the value function whenever they get divorced as a function of their state variables at that time, which include like their age, you know, how many kids they have. But essentially that you don't follow them after you get divorced. So you only use the data while they're married, and you don't use the data after that. That's what people probably would do with this sort of model. Like use them when they're married, but once they get divorced, just don't follow them.
So it seems like constructing an identification argument for a lot of the parameters would be kind of challenging.
It is hard, yeah.
Yeah, so like how much, before you start coding all this up, I mean, do people generally think really hard about the identification, or at some point do they just kind of say, like, this is kind of too much?
So if you think about the last period, that's just a finite model, and anything that's identified in the last period, you know, because if you had data, well, identification is separate from data anyways, but if you just think about the model in the terminal period, a lot of times you can identify everything in the last period. Some things you couldn't, like the discount rate, sort of, but if you only look at people in the last period, they don't have a future, and they're making decisions. I mean, there's certain things maybe that you couldn't because people in the last period don't have that decision. But that's one way I think that makes it easier to think about identification, is think what could be identified in the last period.
Oh wow, so the dynamics really aren't giving you any leverage in the identity. Generally aren't giving you much more identification power.
Yeah, I think,
With maybe the exception of
well, discount rate.
the discount rate and the types, right? The type, it probably helps with the types, but just like just intuition from like a fixed effects.
Yeah.
Yeah.
Yeah, but normally, like in terms of identification, I would just think in last period, like the things where we needed an exclusion restriction and things like that. Like, I think just by thinking about the one period problem, you can see those things. But some things like the discount factor, you saw that you needed functional form assumptions, that it's not like non-parametrically going to be identified. Okay, so the large state space, so this is describing, I think I already just described it in words, but the regression approach, where you do the regression interpolation. So the Emax function at time t, so we have the integral over 6 shocks now. So you have to evaluate, okay, so this is just showing you how you would do this when you have 6 shocks. I mean, you basically, you have 6 is kind of the limit, you know, in terms of how many shocks you can usually handle from, but let's say you had a joint normal distribution with 6 normal random variables, and they could all be correlated with each other, but usually people impose some restrictions on the covariance matrix that they're not arbitrarily correlated because it's hard to identify that many covariances. So usually you would put some zeros in a few places in your matrix. But you just draw the shock so D is the number of draws. So you draw from that distribution, and the way you normally do is with you draw from ID normals and use Koleski decomposition to draw from whatever normal distribution you want, right? That would be the approach. But you draw however many shocks, and you calculate what's the optimal utility, like what, for each set of shocks, you calculate which is their max choice, right? So let's say I draw 2,000 sets of shocks. And then for each of those, I calculate what's their maximum, right? And then you take the average over all of those, and that's your Emax. The Emax, that's taking the expectation over all those shocks. So it's numerically taking the expectation. So this is calculating that like 6 variant interval. Right? We're just drawing from the shock distribution and then taking the average. So it's like a computational way of getting the Emax.
In these examples, are the shocks correlated?
Yeah, they could be correlated. So that would be determined by when you draw from the distribution. If you want to allow for covariances, that's fine. And then when you iterate on this problem, you would be iterating also on the covariances.
And that doesn't really imply any additional computational issues, does it?
No, you just have to estimate the covariance.
Yeah.
That's all. Yeah, I mean, in practice, for sure people sometimes put zeros in certain cells to make it a little easier, because it can be kind of hard to separate out the different things. But if you had 2 shocks that you thought it was important, like the one example raised earlier this morning about a preference for leisure and preference for fertility might be highly correlated. So you would just put in a covariance in your matrix. So, Okay, and then the interpolation function would be, because the state space, that its size is huge, and so therefore you would, draw k state points, and then calculate the Emacs at each of those state space elements. So these are like hypothetical people, because this has nothing to do with data. We're essentially drawing hypothetical situations that women could find themselves in. Hypothetically, they could have 5 kids, and they could have experience of 17 years, and so we draw these hypothetical state points, and then run this regression of the Emaxes that we just got from the earlier slide on the state space element. And then when you go then to time period t minus 1, and you need the Emacs for these actual situations that women are in, you can interpolate. You can use this regression function as the way of getting the Emacs for any woman that's in your data. Like when you form your likelihood. So you have to, if you run a regression at each age, you have to store the coefficients from that regression. Because you're going to need that when you do the likelihood. Okay, so there are you can see there are a lot of just like different parts that go into estimating these models, but it's, there's nothing really hard. It's hard for the computer. And of course, these models, they're not in Stata. So you have to kind of know how to program them yourself. I mean, I've never tried to program in Stata, but I think it would be really hard. So I usually use like Fortran, because you want a language that's pretty fast. Because you see, like here, you're looping over D, right? So you need something that can do loops quickly.
Yeah, and then so is Fortran a lot more efficient than MATLAB when it comes to those kinds of loops? Is that?
Well, I think like people usually use Fortran or C, and definitely people also use MATLAB. And I think they have a way of compiling MATLAB. Chris, you use this, right? Like where you can.
I mean, generally, you can trick MATLAB into doing this fast, but for the most part, MATLAB is. I did something 100 times slower.
Oh, when you say trick, you mean like
yeah, it's sort
figuring
of
out
like when it does a
tricks.
loop, it like reprograms it every single step of the loop. Yeah, so there's ways to make it faster, and if you're smart about programming and you can take care of, you can get everything to vector and do it, treat it as one big matrix and do everything at once, it works great. But for a lot of these problems, it's hard to do that.
Fortran's pretty good at like just pure number crunching, but I think like C is probably just as good.
You only need to learn Fortran once, too, and you know if it. The investment for learning a compiled language like C or Fortran, I mean, it's worth paying.
Yeah, because it opens up this whole new toolbox for you that you can estimate all these sorts of models.
So at this point, like, is Python becoming more popular?
I heard it's popular around here.
I tried Python. I just did something with Python a month ago, and it took me a day to estimate a probit model. So I'm sure that I didn't program efficiently, but
okay.
But
Nice.
that was enough that it's fun to play around with stuff, but if you're doing serious estimation, but you can combine those. You combine MATLAB or Python with C and Fortran, and that's where you kind of get the best of both worlds.
And then the other thing that actually speeds this up a lot is to use parallel computing. So like clusters, and then they have optimizers that automatically parallelize. So you can estimate, like the simplex method or something, you wouldn't normally program that. You just use an optimizer, like a package that comes with whatever software. I mean, they have a simplex routine for Fortran, but they now have these optimizers that automatically parallelize. And what they do is they solve your model. So all you have to do is give it a code that takes as input parameters and spits out the likelihood function. And it can be written in whatever language you want, like Fortran, C, Python probably works too. As long as you have an executable that reads in parameters, gives out the likelihood. And then you can use these parallel optimizers that then spread it out over many machines if you have a computing cluster. So like when I estimate these models, we have a cluster that has like 232 processors. And so you can run 232 sets of parameters at the same time. So I can get, in the time that would normally take for one likelihood, I can do 232 likelihood evaluations. And that speeds it up a lot, actually. So it's making it possible to estimate models that before we couldn't estimate at all. So a lot of places are now using these parallel computing optimizers to do that. And then the nicest part is you don't have to know how to program in parallel. Like when I started using this stuff, I invested some time learning like MPI, which is a parallel programming language, like message passing interface. Which works, and I mean, it was worth the time. It's actually kind of fun to be able to pass messages between processors. But now they have these parallel optimizers where you don't even have to know MPI. Like you don't have to know anything about how to do the parallel stuff. It's all automatic. So our grad students are all using this. It's not hard for them to learn. Okay, so this random interpolation makes things easier. The likelihood, so the likelihood now, when you have, you're simulating things, now drawing the shocks through simulation, what we would normally use is simulated maximum likelihood as well. So let's see, this is, I mean, in the end, the likelihood is the same as we had before. It's the probability of working and the wages and the probability of not working. But now, remember, it's not additive errors. So now, this is the notation like we had before. This is the set of unobservables that induce you to choose option, I don't know why it's HM, but that has two subscripts. Oh, okay, yeah, this is the working decision and this is a fertility decision. So this is the set of unobservables that induce you to make a certain choice. Okay, and so that's how we could write the probability that you choose not to work and not to have a child. That would be this. Right? This is integrating over all the values that induce you to make that choice. And so the integral can be simulated, and that's where you draw from the shock, and then this is just the number of times you observe that the person makes that choice. Okay, and that's your simulation of the probability of making that choice. So it's a simulation method for getting these probabilities that then go in the likelihood. Remember before in the other model you had these normal CDFs and normal densities, and there was actually this closed form. But now, it's too complicated to get closed form. So, but you can do this through simulation pretty easily. Right? So you just simulate for M draws, how often is it that a person actually makes that choice? That's the probability under that set of parameters that they make that choice. Okay, and so this would be the probability of working. So for someone who's working, you also see their wage, right? So the likelihood is not only the work choice, the fertility choice, it's also the wage. Usually the way we would do this is write this as a conditional likelihood, probability of working and having certain fertility choice conditional on a wage, and then the probability of seeing that wage conditional on the state space. You separate out into those two pieces, and that's what goes in the likelihood. It just makes it easier. Okay, so if this is the wage equation, that's the same as we had last time, right? So this is a probability of working given the wage, and this would be the probability of the wage. I guess for some reason I left off the fertility here. But this would be that part of the likelihood for someone who's working. So this is this is given the wage is equal to a certain amount. So this is the wage error, that's equal to a certain value. This is data. We see their actual wage, right? So these are for people who are working. You see their wage. So here, you can calculate this density. This is normal. Okay. So this is just what the different pieces of the likelihood are. There's one thing that I should mention. Oh, the likelihood's a lot of times not smooth, so you have to use some non-derivative methods. So frequency simulators. So there's this old literature on that McFadden had some papers looking at if you estimate, say, just a probit model, you can use simulation methods to estimate a probit model, where you just simulate the utility of one option versus the other option, like you draw from the normal, and then you just count how many people in the simulation choose option 1 versus option 2. And some of those methods tended to not work very well when the probabilities got close to 0 or 1. And you needed very large numbers of simulations in order for the simulation to be accurate. And so McFadden proposed what he called a smooth logit simulator. And this is used all the time, actually, in this work. And the reason is that when the probability goes from 0 to 1, like you have a change in the parameter, and there's a very steep change in the probability, right? Just 0 to 1. And you can smooth it out and make it continuous. And doing it this way actually just makes the approximation more accurate with fewer required numbers of simulations. So it's very common for people to use this. And it introduces this little parameter called tau, which is a smoothing parameter. So this compares this is the choice that would have been maximal. So let's say the probability you choose to work this amount and to have a child in this period. So you compare, this is the utility or the value function for the choice that was made. This is that choice. This is the value function for the maximal choice under your model, right? So this is whatever your model says should have been optimal for that person, and then this is what that person actually chose. So you're trying to minimize the distance between the value function for the choice that was made and the value function that would have been maximal. Okay, and this tau parameter is, ideally you want it to be small. Setting tau is a little bit of a question, like how you set tau. Usually in the beginning I set tau a little bigger, and then, because this is kind of a tolerance, how much different people will weigh into this. I usually set tau a little bigger at first, like when I get the estimation started, and then as it looks like you're getting closer to the parameters, usually make tau a little smaller. But this is the frequency simulator that McFadden originally proposed, just in the context of a probit model. So you may have seen that other paper. This is a very famous paper of McFadden. So that's just kind of computational tricks to help you solve these models better. Okay, now everything I talked about was maximum likelihood, and there are all these other methods too. I keep forgetting I'm attached. So there's simulated maximum likelihood, and that's analogous to GMM, where you basically have to choose a set of moments. I prefer maximum likelihood when possible, just because I think there's less arbitrariness about what the moments are. But as I mentioned earlier, that if you have missing data, it can be hard to integrate out over to miss things. And that's, I think, one of the main reasons people use these alternative simulation methods, like simulated maximum likelihood. Indirect inference is another method people use. But of course, there you have to specify what moments you're going to use, and it's hard to tell. Like if if you use the moments that were the first order conditions from the likelihood problem, then it would be the same. You know, if you had an optimal weighting matrix and those were your moments. So I guess that can provide some guidance as to which moments to choose to think about what would be the moments that the maximum likelihood problem would give you. But I think it's hard to know for sure if parameters are identified, you know, given the moments that you chose. So you have to, you know, think about that, whether you have enough moments to identify all the parameters of your model. But this is also popular, so I wasn't going to talk a lot about this. There's a nice book by Guerriero and Montfort, like all about simulation methods, and he reviews a lot of different methods. Because there's some simulation methods simulate choices 1 period ahead, or you may simulate from the initial conditions the whole lifetime of choices. So there's also a question of how many periods ahead you simulate. So I think the main barrier to estimating these models is mainly computational. And maybe, you know, programming knowledge or something, that there's no package. You know, because usually there have been some attempts to write generic code, you know, thinking that people could fit all different types of models into the generic code. But I think by the time you understand how this is supposed to work, you could have already just written it yourself. Because I think it's very hard to write a generic code given the variety of problems that people work on. So I think you do just have to make a little bit of an investment to learn some programming when you estimate this type of model. Okay, this is another method which is aimed at simplifying this calculation, the Emacs, because that's one of the big computational burdens. I just wanted to mention it because it's being used a lot lately in I/O, you know, so it's kind of had this resurgence of interest in this method. And it doesn't, well, I'll describe it for extreme value because you can kind of see how the method works under the Rust assumption about the errors being extreme value. Although they have recent papers, this is their original paper, and then like Hatz and Arcidiacono have a recent paper, I think. No, Miller and Arcidiacono, right? Miller and that is generalizing the method. So, but I'm just going to describe the original form of it. So this was what we had earlier under the Rust assumption. You could write the Emacs expression in this way, and this is the probability that you choose, say, the working option. This is going back to the simpler model that we looked at first. Well, you can see that from here, if you knew this, the probability of working, you could derive the Emacs expression, right? And so the idea of their approach is you can estimate this non-parametrically, right? So think of a small state space, because then you could just look at the fraction of people working at different state space elements, and that would be a non-parametric estimate. And then from there, you can get the Emacs, right, directly. So you don't have to solve the model backwards or anything. You know, you can just do this mapping. And now if we go to the previous period, t minus 1, well, now we use the Emacs that we just got for period t. And again, we get the probability of working for t minus 1 for the different state space elements, but then we can get the Emacs for t minus 1. You know, so you can back out all the Emaxes in this way. And there's no like integration or, you know, computationally it's a lot simpler. And that's the basic idea, that you could get the Emaxes in this way, and then it has the advantage that this estimation could be non-parametric, you know, if you had a manageable size state space. So you continue substituting in this way, and then you can determine, once you have all the Emaxes, you can get these cutoff values, and then you can, those are the ones that enter the likelihood.
So with a lot of things in applied work, there seems to be a lot of aesthetics, and things kind of go in and out of style. Like, I mean, like, do you have any sense that, like, you know, so some people prefer the kind of logics, and some people prefer the normal distributions, and it kind of goes back and forth, and now, you know, this thing. So, I mean, can you kind of comment on like these kind of trends in the literature? Do you have the sense that they're kind of motivated by what really is the most efficient way, or
No, like I think a lot of it is who was your advisor.
Yeah.
Because you have these different methods that different people came up with, and anybody who works with like Ken Wolfen, they all kind of do it, normal errors, not necessarily additive, and then people in the Rust tradition, there's a whole bunch of people that do the literature errors, and so I don't think it's really for efficiency reasons. The reason this method has had a resurgence here, because this is now a pretty old method, and they extended it recently, but I don't have any slides on it, but they're trying to incorporate unobserved heterogeneity, like these fixed types. Because that used to be a big criticism of this approach, that it didn't allow for unobserved heterogeneity. So they have an extension, and that's the work with our city Econo. And I think they are also doing non-additive errors, or different functional forms of errors. Now additive, you might still need additive, but I think they relaxed that it doesn't have to be extreme value.
I think they did continuous time.
Yeah, they have a bunch of different extensions. But the reason this has been now popular in I/O work is there's work in I/O estimating dynamic models with multiple agents. So these are firms, multiple firms making decisions in a dynamic environment, like about pricing or something, and then reacting to the decisions of other firms. And those models, the state space, I think, can get very large, and like everything here, even though it may look complicated, I think it's simple because it's single agent models still. And in that literature, I think this is a major simplification for them. I haven't myself estimated, but that's why these methods have been used a lot recently in I/O to estimate those sorts of models with the multiple agents.
And to kind of follow up, so do you have a sense that should this kind of case then, depending on advising tradition you come from, do these things kind of play out in terms of getting things published? I mean, is it so finely rooted as that oh, this guy's doing it this way, I am less inclined to,
No, I don't think people would be that critical. People would complain if you had no unobserved heterogeneity, probably, and probably your model wouldn't fit that great, because people bounce in and out of their choices a lot more. But they're even, Steve Stern does some methods that combine these logit errors with normal errors, like logit and normal shocks in one model. So I don't think people are that critical in terms of refereeing or anything that they have strong views that it should be logit or should be normal. Because people appreciate these models are pretty hard to solve, under either type of assumption. And that's just a modeling choice. It's kind of like choosing the function form of utility function. Of course, the additivity is a restriction that you wouldn't need to impose under some of the other methods. Okay, but this is called a CCP approach. It's conditional choice probability. That's what the CCP stands for. And one thing is that in order to do this approach, you actually need data that corresponds with all the time periods. So remember, in the other approach, you could have a model of 65-year-olds, and the oldest person in your data could be 30. You could estimate your model even up to age 65. You didn't really need the data on 65-year-olds. But here, because to get these Emaxes using the CCP approach, you need to be able to estimate the probability of working at each age, because you need to at all those different state spaces. So either you need to observe people over a very long time period that covers all of your model, or else you need to have kind of overlapping ages in your data. That your data has the different ages, although not everybody may be observed over the whole time. So it's kind of a synthetic cohort approach. Okay. So Arcediaco and Miller are developing these methods for unobserved state variables. And then the other thing sometimes in terms of this model makes it easier to get the parameters because you don't have to, do this Emax solution. But sometimes you don't get the distribution of the unobservables. You know, like you're non-parametric about the probability. And oftentimes when we want to do policy simulations, like let's say you want to simulate the effect of child care subsidy on fertility, behavior, and everything, to do that simulation, a lot of times you need the distribution of the unobservables. So even though this is like a shortcut for getting most of the parameters of the structural model, if you don't have all the parameters, you may not be able to do some of the policy simulations that you want to do. So maybe you could use this to get most of the parameters, and then in the end, you still have to estimate the distribution of the unobservables. But there are a lot of papers just, you know, on how you estimate these models and different ways of doing it, which I guess it gives you a lot of variety of options, but it also makes the literature maybe a little harder to read because, you know, it looks very different if you do the logit approach versus the normal approach. Okay, so I wanted to I see nothing here on this screen, it's totally blank. Oh, you just have to touch. Okay. All right. Yeah, I wanted to open like this. Oh wait, this first this again. So I put like a sample, this is like a sample problem set. I wonder if there's a way to make it a little bigger.
What time is it due? What time do you want them to hand it in?
Yeah, for over lunchtime if you work at this. Well, it's just a sample in case you want to try out this yourself. And I also put it the program that does the dynamic program for this problem in Fortran so that you have an example. And the way you had before was good. Yeah. Okay, so it's a model of just a woman making fertility decisions where you would just set some parameters in the model. Yeah, this is just something I give out of the problem set in my graduate class. Actually, I had an undergrad doing an independent study, and he had to do this too. He was a really good undergrad. Okay, and it's assuming that women have perfect foresight over husband's income. So there's only one shock, which is just the fertility preference shock, just to make it easier. And then it just says pick some parameters, and then simulate fertility decisions. So a good learning exercise is where you do a model, you simulate data from the model, and then you write the code and you try to recover the parameters from your original model. So that's like the analogous to Monte Carlo type study where you know the truth, and then you see if your code can recover the truth. Right? And that's what this problem set is, that you just fix some parameters, you simulate fertility decisions, and then you can do simulations where you say, well, now if the husband earned more money, how would fertility patterns change? You know, because here the husband's income is increasing over time, right? And there's a cost of having children, so that'll affect the spacing of the fertility. So then you can say, well, if husband's income didn't decrease, if it was flat over time, what would fertility look like? So see, maybe we can open up the other file. Yeah. It's just like a text file. No patch. What else? WordPad? What are the other? There's some other. I have it on my website. Yeah, it is on my website.
Notepad++.
Yeah, I don't think it's
It just seems, see if I can. So this was just, I put the program on here. Oh, here it is. Okay, so this is just the beginning part. These are just routines to draw random numbers. You may not need this, like to draw normal random numbers. So it depends what kind of Fortran you have. You know, so a lot of them, the random number routines are built in. You don't actually have to supply them. And then this is just a sample program. And so it basically does the problem stuff, but it doesn't do the maximum likelihood part. So it only does the solving the model part. So it just sets the parameters, the alpha values. When you draw random numbers, you have to set a seed for the random numbers. It sets the variance. Remember, there's only one shock. It draws all the shocks in the beginning. That's usually more efficient than drawing them over and over. And then here's the loop where it's solving backwards. So 20 to 1. So that it was supposed to be for women up to age 40, but each time period is 2 years. You know, because you don't usually observe 2 fertilities in 2 years. So it's like every other year. And then the state space. So what's the state space in that model? If you have a fertility model, what would be the state space? Louder, I think.
Whether you have a kid in each age category and whether you're working or not in your...
Well, here the woman's not working.
Husband's wage.
Husband's wage, yes, she knows her husband's wage.
Number of kids.
Yeah, number of kids, that's the only really important thing in this model. Her utility depends on her number of kids. Because otherwise her age, husband's age is in the state space, and then the number of kids that she has.
So can you deal with the composition of kids' age? Like if it's some kind of
You
math?
could, but that would be more complicated than for a problem set. Okay, I just wanted them to be able to do it.
So you kind of don't want to deal with his history, right? Because
Yeah,
otherwise
you
you have
could-
to keep track which year you have each kid.
Yeah, you could keep track of
Then-
when the kids were born, and then you could figure out how old all the kids are. Yeah. And so that's what this S is going over, all the different possible state space values. So 0, you can have 0 kids up to 8 kids. That was the max number of kids you could have. So you get income if you don't have another child. Let's see. This is, and then if you do have another child, those are the two. So this is just, you want to compute utility with child and without child. So if you do have another child, you subtract the cost of because the number of kids you have would be augmented by 1. So SR is equal to, that's just the real number. Fortran, you have to worry a lot about whether your numbers are integers or reals, you know, so you have to convert. Actually, this is, if you do double precision, you need to have like D-0 and so this is utility with no child, and this is utility with child. Those are just from those utility functions that I had written down. And if not the terminal value, then you need to get the Emacs function. So this code is getting the Emacs function. If it's in the terminal value, then there's no future, right? Like if you're in the last period. If you're already at 8 kids, there's a constraint that you can only have up to 8 kids. Then you get utility without a child because you can't have a child. If you have fewer than 8 kids, then you get utility, the max of without a child or with child. So this is the max of utility. And now to get the Emaxes, because it's solving it backwards. So this part is calculating the Emaxes. Even though for this problem you could have done the closed forms and everything, I actually did it just using numerical integration. Because it's easier, I think, and it's what you would do anyways if you had more shocks. So this is just taking 100 shocks and taking the average. So see how we're just adding up the maximal utility, and then at the end we take the average, and that's the Emax associated with that state. So in the 20th time period, we take the utility, the max of the utility, and then do that for a lot of different shocks. So this is actually a vector. I should have mentioned that. This was doing it for a whole vector. And then take the average, and that's the Emax. So this little program actually, gets you the Emaxes. And then if you're not in the last period, then you use the Emax from the previous period. Right? So this is using the Emax from period I+1. So if you're in the 19th time period, then it uses the 20th period Emax. And if you're evaluating utility without a child, then you evaluate the Emax with S staying the same as it is today. If you evaluate utility with a child, then you get the Emax with S being augmented by 1.
Instead of looping over the shocks, you could have vectorized it, right?
Yeah.
To make it run.
That's what you mean?
So instead of looping and calculating, you could have done it this.
Probably, yeah, that you could vectorize. Let's see what this max U. In the beginning, in Fortran, you always have to specify the size of everything, right? Yeah, so my max U is 100. So it is a vector of length 100. So when I draw the shocks here, and then this part is taking out the relevant part of the shocks, the ST1 to ST2, which looks a little bit weird, but this is just taking out for the different time periods, the whole vector of shocks. This EPS vector, this is a vector of shocks. And these shocks were normal 0, 1, so to get it normal 0 var x, you just have to multiply by the square root of bar x here. So it is vector actually already, the way it's doing it. This is a vector. So really what this part is, it's only taking the mean of the vector. Now I think there's actually a mean function in Fortran. I probably could have used the mean, because there's an automatic mean function in Fortran, or average or something. I just didn't use it, I just kind of took the average. Because max U is already a vector, and so it's just taking the average. Okay, but that's kind of the basic structure for this very simple model with one choice. It's doing the numerical integration over the one normal shock, just for illustration, and solving the model backwards, storing the Emaxes. But the problem said to do the likelihood part. So I didn't, the next step would be now that did I do the likelihood part? No, this is a different. So this is, then I actually simulate behavior. This part of the program takes the solution to the dynamic programming problem and then simulates the behavior of women so that under different sets of parameters you can simulate. Once you have the Emaxes, you can now go forward, like starting at the beginning of our lifetime, you would simulate choices. You need new shocks, so we have to draw new shocks now, but we're going to simulate choices for many different women over their whole lifetime. And then you can see, if you vary the income process, how is that going to change how many children she has, things like that. So if you're interested in these methods, I would recommend that you try to compile the program and just to get a feel for how the decisions change as you vary parameters. Like this there are a lot of interesting problems that only have one choice. Like you could do the choice of when to exit school. You know, like do you keep going or do you drop out? The choice of working, you know, so there are women's work, labor force participation. So there are a lot of problems that are pretty manageable, you know, that you can do without, you know, having to wait a whole year for the function to iterate. So, and I think the best way to learn how to do it is just to try it out. You know, you need a Fortran compiler, compile it and just run it for different parameters, you know, see if you can program for a simple problem you're thinking about, like not fertility, maybe some other problem, try to write a program for it, you know, and specify utility function. Okay. So we have just a few more minutes. We go to 12:30, right? Or what?
Yeah,
12:30. So I have these other slides. But maybe I'll just kind of go over, since the theme is inequality, maybe I can mention briefly the paper that I have where we use this type of modeling approach to analyze questions related to inequality, you know, because I haven't said a lot of things specifically. Since we won't have time to talk about this very much, we do a little bit like what you can do with structural model non-parametrically. So this is based on this other paper I have with Ken. So if you're interested in that, I can give you some references for that. And then I have a few examples. So we did this survey of applications of dynamic discrete choice programming model in development. And I mean, there are not yet a lot of applications. I mean, the development literature does a lot of field experiments and things, and so there aren't yet that many applications. So these were all the ones we could find at the time we were writing the survey. And since then, there have been a few more, but not that many. So I want to describe just this one application I had with, this is David Bravo at University of Chile, Dagtar Mukapate, who is a former student from Penn. He's at Nevada. Just to show how we looked at this to analyze questions related to inequality. So we were studying the school voucher program in Chile that was implemented in 1981. Chicago, University of Chicago was heavily involved in this. This was Milton Friedman had proposed school vouchers, and this was under the Pinochet regime in Chile, and they adopted a few reforms that were like deregulation types of reforms. And one of it was a school voucher where it's called a funds follow the child voucher design. And so there are 3 types of schools, and this system persists today. Like, it's remarkable that it's actually survived all these different governments, and it's still basically the system that Chile has today. They have public schools, they have private schools, which are called subsidized private. And those are private schools that accept the voucher as payment. And then they have some non-subsidized private. Those are very expensive schools that do not accept the voucher. And only a small fraction at 10 seats. And there's free entry, so people can decide what school they want to go to. Public schools have to accept people, like the students who apply. Private schools don't necessarily have to accept people. They can have some standards for acceptance, but they do have to accept the voucher. And then teachers have to be licensed in all types of schools, so there's some teacher requirements. So in this paper, we want to see how did this voucher reform affect schooling decisions and labor market outcomes? And also on inequality, like did it make the education distribution more equal or not, and how it affected the income distribution. And so we estimate a dynamic model of schooling and working decisions using this longitudinal data for Chile. They actually have now 2 more waves of this data. It's a very nice data set. One of the few longitudinal data sets for Latin America. There's no variation in the timing of the reform, because the reform came in, everybody was exposed. So there's no group that got treated and didn't, like everybody got treated. But we use the fact that people were at different stages in their schooling career when the reform came in. Right, that's the main source of variation that we use.
Maybe you mentioned, but who gets the voucher?
Oh, all the students, yeah, everybody gets the voucher. Yeah. So it's not like in the US where you have to go to the school in your neighborhood or anything. Everybody gets this voucher and they can pick their school. And the parents also get lots of information about the schools. Like nowadays, they actually send stuff to their house, like comparing the performance of the different schools to help them make more educated decisions.
Can people pay more than the cost of the voucher? Or more than the voucher to the school?
Well, the schools are restricted. Like now they're allowed to charge a small tuition. Initially, they weren't allowed to. Now they're allowed to charge a little bit, but they're very restricted how much they're allowed to charge. Yeah. Okay, so we want to see how the reform affected inequality, and mainly looking at education and earnings outcomes. And the type of model we write down is the types of model Chris will talk about this afternoon. It's kind of an example of a dynamic version of our Roy model. So in Roy, you get occupational choice. Here we have, education choice plus whether you work or not. But the general framework is kind of a Roy model. And we allow the returns to education within this model to depend on what type of school you went to. So if you went to a public school versus a private school, the returns can be different. And then also if you went in a pre-voucher regime versus the post-voucher regime, the returns can be different. Okay, so the basic structure, like age 6 to 15, they decide whether to go to school or stay home. And then after 15, they start also getting wage offers. So they can decide to leave school and enter the labor market. They also decide what type of school to go to, like public school, private school, or private non-subsidized. Those are the very expensive schools. And then they also decide after they graduate high school, they can attend college for up to 5 years. Okay, but at age 16, they start getting wage offers, so then they could drop out of school. And the wage offers depend on years attended, whether attended pre or post voucher, and work experience, which is endogenously accumulated the way we had in the example. The H, it's like that. And then they retire at age 65, so we don't really do much with the leading. Okay, so here you can see the types of simulations that we got based on this model. Okay, so we estimated the model assuming the voucher program came in and it was a surprise. Because in the real data, there was a voucher program, right? And so we're going to simulate the counterfactual of no program. Because in the real data, there was a program, but we do have to decide when we're solving the model, was the program a surprise or not? So we assumed, and this usually you have to have evidence, was it discussed in Congress or somewhere? But at this time, it was pretty much a surprise, I think. So, you can always say they knew about it 2 years ahead of time. That wouldn't be hard or something to put in. And then we simulate, we take away the program, and we say what would have happened, right, under this. And then we also do it by poverty status of the family, because one of the criticisms has been that the voucher program only helped the wealthier people, so it didn't necessarily reduce inequality. So this is the percent attending private school went up a lot. That's what we're saying happened. This is percent attending non-subsidized, but actually some of the people that would have attended the more elite schools switched to attending the voucher schools. And this is both true for private primary school and secondary school. And then college going went up, we're simulating. So even though the voucher program only applied in high school, if people get more education as a result of that program, that also can affect their college going behavior. So, and then when we break it down by poverty status of the family, the results are pretty similar across the different. We had, I think, 3 types, unobserved types in this model. I didn't bring the full statement of the model because I didn't think we'd have time. And then this is the earnings of workers. So one thing is with the voucher program, people stay in school longer, and so while they're in school, they're earning less. So the earnings of the workers, they don't go up that much, and it's partly because, well, this is for different age groups, so this should actually be this line here. You can see that with the program, the earnings of the youngest workers is slightly lower. And that's because they're staying in school longer, and so they hit the labor market later. But then, and so they have less work experience. So there wasn't a huge gain in terms of earnings. Percent of time participating in the labor force, without the program, people would go to work earlier. And then I think for older people, they worked a little bit more with the program because they had more education. And then, so in these models, when you estimate a utility function, you can look at welfare.
Yeah, so is this kind of situation where it would be really useful to have like a general equilibrium effect because you're having such a big impact on the supply of different varieties of educational attainment?
Yeah, I think it would be a context where it would make sense to introduce. We tried to allow for some business cycle effects on, I think how we put this. It was just a few years.
Yeah, it's because wages are so, when a cohort of a generation increases, that has a big impact on the wages they receive.
We did allow for the type distribution. The other type distribution changed with cohorts. So there could be differences over time just in the types of workers.
But yeah, it would affect the wage offers.
Yeah, it affects the wage offers. So different cohorts of workers could just get different wage offers because they were in different environments over time. But the data, we only have wages for present day. We don't have a lot of wage information. We actually do have labor force participation information because they answered retrospective surveys. So we know back to 1980 their whole work history. But we don't know their whole wage history. So the wages that was kind of a big limitation of the data, that we didn't have the wages going back that far. An unusual feature of the data is we know what type of school they went to, pre and post voucher, because they wrote the name of the school on the survey. So that was unusual to have that. But so we had much better data on labor force than we had on wages. Wages was present day. So that's why you couldn't do that much with the stocks of different types of workers affecting wages because we didn't have wages.
Yeah, so they don't even have labor force surveys where you could.
They have some different surveys,
Right.
You'd have to get it from other data. But I don't think they go back to 1980. But then you could also look at effects on utility, right? Because if you estimate a model where you have the utility function, the nice thing is you can look not only on wages, but also on welfare. Discounted lifetime utility with the reform and without the reform. And we were finding that even though there were not big changes in wages, there were some changes, inequality did not go up a lot. So that was a big concern people had, that it actually increased inequality. But we're finding that utility did increase pretty much across the board. It's partly because people get more utility from going to school than working as a young person, and you get that in the model. And so therefore, even if wages don't change a lot, you can get changes in utility. So we're finding it did increase utility. All right. So we didn't get to do quite as much as I had intended to, but I guess you'll have the slides that were included. Feel free to contact me if you have questions about other aspects of the slide.